Good evening, everybody. My name is Giridhar, and it's a pleasure to welcome you all on behalf of Azim Premji University for this public lecture. This is Arthur's third public lecture in every consecutive January. So it's virtually a much looked up to and sought after event for us. We begin the new year public lecture with Arthur's lecture, and it's a delight to have you once again with us, Arthur. Claps. Go hard with both hands. Because I must tell you that science and science education, probably Arthur is one of the friendliest and warmest faces in science and science education. And I can say that from personal experience because each year he comes here and spends time with a cross-section of teachers, teacher educators, our own people in the foundation. And at every time he makes science wonderful and science teaching look so possible and so exciting. The art of making science interesting to us in the kind of topics he chooses. And today it's about sports on the moon. So when a month ago or 2 months ago when Arthur told me that science on the moon is his talk for today, for some strange reason, I remembered a movie I saw in the 70s called Absent-Minded Professor, where it stuck something on his soles of his shoes and could basket everything in sight. So for some reason, I went into that and I thought we'll have something wonderful from Arthur today as always. It's an event that we look forward to, and Arthur, it's a pleasure to have you. The other event that we have great pleasure in combining this with is the launch of the science magazine from the university called I Wonder. I Wonder is now the fourth or fifth of our magazines from the foundation. 15 years ago when the foundation started, the first publication from us was a rag, a 4-page newsletter, which said we did this in Gulbarga and we did that here and so on and so forth. But from that small beginning, some years ago, we started what is known as the learning curve. And the learning curve is into its 25th year of 25th issue now. On the way, as we went along, we also created a math magazine called At Right Angles. We have partners who produce a magazine called Language and Language Teaching. And we also have great pleasure in partnering with Usha Raman in Hyderabad for the Teacher Plus, which is a monthly magazine. About a year ago, and here I would invite Ramji, my colleague and friend. Ramji, who managed the publication for us for the past few years, had this junoon that we must come out with a science magazine. And all he needed was lag jao. So there it is, you have in front of you a magazine that I told him looked sumptuous and rich. But I think behind it all was a huge passion that we must bring out a magazine. And if there's one thing that Ramji and Arthur share, it is that cheerfulness with which they embrace science. So Ramji, a pleasure and a beautiful day for you when you have the launch of I Wonder by none other than Professor Eisenkraft. I have not done the formal introduction of Professor Eisenkraft because many of you know him, but to me, although you have read it all, to me I would once again repeat that we couldn't have a better person than Professor Eisenkraft to release a science magazine which will be used by teachers and teacher educators. Thank you.
So it really is a wonderful occasion. I Wonder is an extremely special magazine. There are lots of places in which people can find out how to be excited about science. You can read many books, articles. This magazine is for middle school teachers. And what makes it different is not just the high quality of the authors and the articles and the wonderful illustrations, the diverse interests, whether you're learning about blood or learning about nerve cells or learning about optics and color. But there's also the nature of science. There's the student misconceptions of science. What teachers need is not just to learn the science and be engaged in the science. What they also have to do is how to translate that to the classroom. And so I Wonder not only captures the beauty of the science and the information and the quality of learning with a biography of J.B.S. Haldane and an interview with a scientist who lives today who can serve as a role model. But there's also this bridge. How can middle school teachers use this in the classroom? Now, it's for middle school teachers. It's available on the internet. It's also for everybody else. So everybody can read this. I can read it and enjoy it as well. I think we're going to start a campaign, though, saying children cannot read this magazine. You're not old enough yet. Don't read this. The stuff in here is secrets, only for adults, only for middle school teachers. Children, stay away from this magazine. It's too much for you. You should not read it. And this might encourage them to read it as well. So let me introduce Ramji, who's the co-editor of this magazine with Chitra, the other co-editor, who knows much more about it than I do and is responsible for this I Wonder wonderful magazine.
Thank you, Arthur. So it took actually 9 months to produce this baby, you know. So it was a tough one. All we had was a lot of passion when we started off with. And then very luckily, there's so many people who volunteered to become part of the editorial board. And we managed to put together a fantastic team to actually make this happen. So from the beginning, our idea was that this would be aimed at as a resource for the teachers, middle school teachers, whom we work extensively with in the foundation. However, we wanted it to also be a platform where the teachers can share what they have tried out in the classrooms, which have worked beautifully to explain a theme in the science, etc. We also wanted to break this paradigm that science is sort of unidisciplinary, which is what typically happens in our schools, that you learn a theme under a particular subject, either physics, chemistry, or biology, and then you stick to it. We wanted to ensure that the students really know that there is so much of beauty in learning the 360 degrees around a particular concept. So the first issue, the theme for this issue is interdisciplinary science. And like this, we hope that every one of these issues which we come up with would have themes which are a little unique, which does not get covered in our existing curriculum, but which strengthens the teacher's knowledge and helps them explain certain themes far better, knowing the interconnection between multiple themes and multiple subjects for that particular theme. So thank you so much. I hope that all of you are huge science enthusiasts. I hope that all of you will end up contributing to the magazine somewhere down the line. That's really what we are hoping will happen, so that there will be a wide circulation as well as a wide contribution to the magazine. Thank you so much. Giri? Yeah, so like all our magazines, this is available for free download on the university website, azimpremjiuniversity.com. And you can download this as single articles, or you can download the whole thing as a larger PDF. And we hope that that's the way we'll reach maximum number of teachers who can then print it out, use it in their classrooms, etc., etc. Thank you so much.
Well, thank you. Thank you so much for coming this evening so we can talk about this idea of sports on the moon. I'd like to know first who you are, just as the caterpillar wanted to know from Alice in Wonderland. So in terms of science knowledge, physics knowledge, zero means I know nothing. Nothing. It means if I let this go, I don't even know which way it will fall, whether it will go up or down. I know nothing about physics. 10 means I know everything about physics. There's not a question you can ask me about physics I can't answer. So I'm going to ask you, how many people are 0 to 3, 4 to 6, 7 to 9, or 10? So how many people would say they're 0 to 3 in terms of physics knowledge? Okay. How many people would say 4 to 6? 7 to 9? Okay, so we have a couple of physics people here. And 10? Dare anybody say they're at 10? Because nobody should say, the best Nobel laureate should not say 10. There's always something to learn about. So, okay, thank you so much. Oh, and how many people are teachers? Lovely. Okay. So, my nephew came over the house, and it was raining outside, and he said, I said to him, what do you want to do? It's raining. And he said, I'd like to watch sports on television. I said, all right, we can watch sports on television. And I turned on the television, and this was on the television. I said, how's this? And he said, that's not sports. And I said, oh, that's not sports? Okay. I turned the station. I said, here, now we'll watch this. This is sports. And he said, no, that's not sports. And I said, oh. So I said, okay, we'll watch something. How's this? He said, no, that's not sports. And then I turned, and he said, yes, that's sports. He saw something on the TV, and right away, he knew it was a sport. So I'd like you to think about two things, just two things you think he saw on the screen that indicated him it was a sport. What did he see on the screen that to him said, that's a sport? Again, not a sport, not a sport, not a sport, and then, it's a sport. So just turn to the person next to you and see if you thought of the same two things. Just talk to your neighbor. Okay, tell me, what was one thing my nephew saw on the screen and he said, that's a sport? What did he see? Cricket. What did he see that he knew it was cricket? He saw the field. He saw a ball. He saw a ball, a field. What else might he have seen? Yes?
A group of happy people cheering.
People cheering. What else did he see?
Movement of objects.
Movement of objects. What?
Running.
Running. He saw somebody running. What else did he see?
He saw only men.
Only.
I am so disappointed. I'm sorry, I can't hold that back any longer. Not a single woman scientist. Not a single
Oh, that would have been disappointing. Yes.
I'm sorry, why are you saying that?
He needs more women in I Wonder.
There are women scientists. There are amazing women
There are so many of them in
There are two writers. I think what you
many writers.
Sorry, I just haven't put that in.
Okay.
But I think I see.
So in sports, there are men's sports and women's sports. Yes. Okay. So here's a cartoon and lots of things. Oh, scoreboards. There are scoreboards and there are balls and people moving and women and men and all sorts of things happening. And this allows you to know what a sport is, different from these other things. One day, we're going to be on the moon. Not just for a few days like we've been before, but we're going to live there. And if people are going to live on the moon for a long period of time, they're going to need to do exercise to stay in shape, and they're going to want to entertain themselves. And sport is one of the ways in which people entertain themselves and stay in shape on Earth, so they'll do it there. So I want you to think, by the end of today, in 1 hour, I want you to write a proposal to ISRO or NASA, which includes a description of your sports and rules, a comparison of the factors on the Earth and the Moon, the comparison of play, and maybe a newspaper article that people back home will read about the excitement of a championship match in your game. So, what must you know to be successful? To be successful at developing a sport for the moon, you have to know something about the moon. And you have to know something about sports. So, the moon is different from the Earth. And you want to know how these changes affect sports, the rules or laws of the sports on Earth. What makes sports entertaining? And how the sport would be played on the moon. The fields, the rules, the scoring. So, we've gone to the moon. Some of you were born after we've gone to the moon, but we went to the moon. And we took photographs of the people on the moon. So let's take a look at the astronauts on the moon so we get a sense of how the moon might be a little different than the Earth. So let me see if this works. Why does he walk that way? Why does he wear a spacesuit? Oh, cars go on the moon. Look at his feet, there are dust on the moon, it's dusty. Oh, that's a different way of moving around. Some of you weren't alive when this first happened. This happened in 1969. A few years later, I was living in Nepal and teaching in a small village there. But somebody came to tell me that, another volunteer, in 1969, when we first walked on the moon, there were people in Nepal who walked 7 hours to congratulate him as an American because we had walked not on the moon, but on the god. We had walked on Chandra. I mean, this was an amazing, you look at the moon in the sky and you say, how do you get there? Are there any signs, any directions? Make a right here, make a left? I mean, the moon is moving. This is quite an achievement. And then to say, let's go there again and we'll bring a car with us so we can run around. So let's take a look at, again, what you need to be successful to develop a sport that we can play on the moon. You need to know how the moon is different from the Earth. I can help you with that. You need to know how these changes affect sports. I can help you with that. The rules and the law of the sports on Earth, what makes sports entertaining, how the sport is played on the moon, you have to do that. It requires your creativity. I can't do that. Different fields, different rules, and that's what I want you to start thinking about. Which sport would you like to play on the moon? Would you like to export cricket to the moon? Would you like to export badminton to the moon? Would you like to export football to the moon? What do you want to export to the moon? And let's see if you can or how it would change. So the first bit of physics we have to know is that all objects fall at the same rate on the moon, just like they do on the Earth. So if I take two objects on the Earth, I take one which has a small mass and one which has a large mass. The first bit of physics we should know is that if I let them both go, they hit the ground at the same time. Now, how many people believe if I let these go, the pen hits first? How many people believe the tennis ball hits first? Or, as I'm saying, they hit the ground at the same time? How many people think that the pen will hit the ground first? Yeah. How many people think the ball will hit the ground first? Yeah, right here. The ball will hit the ground first. How many people think at the same time? You're all such good students. Okay, so let's watch. Good. At the same time, no surprise. Now, on the other hand, if I take something like this, how many people, this is a filter to make coffee. How many people think the coffee filter hits first? The ball hits first? They both hit at the same time. Coffee filter hits first. The ball hits first. They hit at the same time. The book says they hit at the same time. No, you don't think so? Let's see. Oh, yes. The ball hit first. So you have good physical intuition. There must be a reason why the pen and the ball hit the same time, but the coffee filter in this does not hit at the same time. And we say, oh, there's air. There's air. On the moon, there's no air. So one of the times when the astronauts went up, somebody said, let's take a feather and let's take a wrench or a hammer and a feather, and we'll drop them on the moon and see if Galileo was correct, that all objects fall at the same rate if there's no air. So now, they had the hammer. They have to bring a hammer anyway because they have to bang on things when they get there. But the feather was an extra transport. So let's see what happens when they do this. I circled them to help you see. But let's hear.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time.
Boom.
How about that? Mr. Galileo was correct in his findings.
Now, that's wonderful. What I heard, but I haven't, you can find these on the internet. What I heard, but I've never really made sure is correct, is that before he dropped them both in the camera, they said, can you try it once before we do it? So here we go. So now we can do this with photographs. This is just an illustration. But the idea here is that if you notice, they both fell. It looked like it was in slow motion. It was in full lifetime speed, but gravity is less on the moon. So in the time it takes on Earth for the hammer to fall from here to here, on the moon it only falls from here to here. And we can measure the distance it falls here and measure the distance it falls there, or take the videotape from the moon and do another videotape on Earth with one of your, we can now do video slow motion on our cell phones. And what we find is that it takes, in 1 second it falls this far, here it falls, in 1 second it falls this far, to here, 1 second it falls this far, or to fall all the way on the moon, instead of 1 second, it will take 6 seconds. Things fall very slowly on the moon. When you saw the astronaut jump off the thing, he jumped off slowly. When you saw the feather and the hammer, it went down slowly. So what does that mean for our sport? Well, things are going to fall very slow. So here you see an astronaut driving off the diving board, and the other astronaut's supposed to bring the trampoline there to land on. He says, I have plenty of time. He's not falling yet. Oh, they'll take a while. Yeah, so he's just, whistling, just moving along. And so things are very slow on the moon. And so one of the things you're going to have to take into account when you make your sport for the moon is things fall very, very slowly. And that has a lot of other effects as well. Well, now, if things fall slowly, if the moon is pulling things down with a different acceleration than they pull down on the Earth, that means your weight is different on the moon also. So right now, and we have to be a little careful here, there are some people here who have a mass of 60 kilograms. Now, on Earth, we don't care. We call 60 kilograms the mass, we call 60 kilograms the weight, because who cares? We know the difference. But all of a sudden on the moon, it's going to be different. So I wanted to show you this. You see, I have two bottles here. Now, this is a bottle on the Earth or the moon, and I can push it. You could try to push me, we'll say I'm 60 kilograms. You could try to push me on the Earth, try to knock me down, as we do in some sports. In football, we push people out of the way. And we push people out of the way, and we say, okay, it is just as hard to push me out of the way on the moon as it is to push me out of the way on the Earth, because that depends on mass. On the other hand, if you try to lift me, see, I'm 600 newtons on the Earth, but I'm only 100 newtons on the moon. So you might be able, a lot of people here would have trouble lifting me. But on the moon, I'm only 1/6, so you could lift me right up, just lift me right up. So now, I want to just show you this. On the moon, could you come up here and help me? I need you to do something. Now, I want you to just push this back and forth like this, okay? Just do it back and forth. That's on the Earth. Now I want you to push it back on the moon. Same way, push back and forth. Any difference? No. No difference, no difference. Oh, no, that was the easy part. Now I want you to take this, and I'm going to let go, and I want you to lift it up as high as you can, as fast as you can, on Earth. Okay, very good. Now I'm going to give you the same bottle on the moon, and I'm going to let you take it, and you're going to lift it as fast as you can on the moon. Go. Was that different?
Yeah.
How was it different?
The weight was less. Yeah.
Much less weight. On the moon, it's very easy to lift things up. In fact, you could lift me on the moon. Thank you. So now in the illustration, you can see it's just as hard to push that cart, but it's easy to lift it. So now, in the sport kabaddi, we play the game kabaddi here? Okay. So kabaddi, you want to hold somebody, you want to push them, you want to keep them there. It might be easier to just throw them in the air and run underneath them. You throw them up, it takes a long time for them to come back down, and you just run underneath. How is this going to affect your sport? Hard to push, just as hard on Earth, but easy to lift. Okay. Now with the less gravity, you see in the bottom picture, the person is kicking the football, and it goes that far. On Earth, though, on Moon, when the astronaut kicks the ball, oh, that ball goes very far. It goes 6 times further. You'll notice the person on the Earth is looking at the Moon. The person on the Moon is looking at the Earth. So let's take a look at what does that mean, 6 times further and 6 times higher, because gravity is 1/6. So let's do 6 runs on Earth. This is a cricket field. We don't play cricket in America, so I had to go on the internet, and I hope I get this right. 6 runs is where the ball goes all the way out of the stadium, out of the field. So that's a cricket field. You all have a sense how big a cricket field is. So with 6 runs, from the middle of the cricket field, it goes to the outside. And it also takes a few seconds. Oh, the batter hit the ball, it's going, oh, it's 6 runs. That takes about 3 seconds. On the Moon, it looks like this. That's how big a cricket field would have to be for 6 runs. That's enormous. That's enormous. And the play goes something like this. The batter hits the ball. Oh, we're going to break for commercial. And 18 seconds later, we will tell you if it's 6 runs or not. So for some of you who think cricket is boring on Earth, forget about on the Moon. So now if you want to export cricket to the Moon, how are you going to make changes so that the game is still entertaining? You're going to have to change it somehow. You can't have balls going this far and in the air for 18 seconds, but you still want to play cricket. So how can you modify cricket accordingly? Oh, did you notice the astronaut jumping on the Moon? So when you jump on Earth, I want to be careful so my head doesn't hit the ceiling. When you jump on the Earth, you jump like that. You go down and up. When I jump on the Moon, I jump 6 times higher. So now, I knew what 6 times, I think I know what 6 times higher means. But it's not until I draw the picture and I say, well, what does 6 times higher really look like? Because this is me jumping on the earth. And then I look and I say, oh, 6 times higher? That's this. Oh my goodness. Oh my goodness. What does that do to basketball? How are you going to change now, you know, one of the things about basketball is when you watch basketball, when you play basketball, when I play basketball, you know, we shoot the ball, we try to run up, we try to do that, and then we watch the professionals. But don't forget, those professionals are this much taller than me. They're bigger. Their hands are bigger. So when they're playing basketball, for them, the basket is only over here and the ball is only this big. And they're going like this, they're going like this. They can do all this because they're so much bigger than I am. And we forget that when we watch them. It's like, yeah, no, the basket's only this high for them. Boom. It's only this big, they can grab. Oh, look what I do with the basketball. So, but if you can jump that high, maybe there's a good game for jumping. Oh, when you dive off a diving board, you can dive way up, and you have all of this time to do spins and twirls and twists and this. How do you judge diving on the moon? So now we're going to take a break. You see, when I teach this, you've now learned a certain amount of physics. You've learned a certain amount of physics, and your challenge is develop a sport for the moon. So I need you now to take a look at what we've learned so far. All objects fall at the same rate. Objects take 6 times as long to fall on the moon. Objects weigh 6 times less on the moon. The mass remains the same, just as hard to push. Projectiles travel 6 times as far on the moon, and people can jump 6 times higher on the moon. So I'd like you, with the person next to you or a few people next to you, is pick a sport and tell me why you can't just bring it to the moon as is. Well, maybe you can. And think about how you might change the sport so that it could work on the moon. And I'm going to give you 4 minutes to do this, and then you'll tell me, some of you will tell us, I have a good way to change the sport. So you got to work for 4 minutes now. Talk to people. So who would like to tell us a sport? Yes.
Okay, so I don't know. I think it's sort of a little bit of crazy idea. I just want to.
I hope it's crazy enough.
Okay. In that case, I just thought, why not increase the weight of that person by 6 times, and the weight of the ball by 6 times. You could play with your normal same. I don't know.
But
This should be done.
But if you increase the weight of the ball 6 times, it's very hard to push.
I know. I'm increasing my mass as well.
And how do you do that? More musculodosa? I mean, how do I do that? Externally, I'll put on. But will that increase my strength 6 times?
No, it's not the strength. Probably.
Well, tell me a sport. Tell me a sport so we can consider that wonderful idea.
Maybe football.
Football. Now, to kick the football, our young student here told me that to kick it is just as hard on the earth. You've just made it 6 times more mass. Ooh, oh. So we have a problem.
Okay.
But I like the idea, and we have to keep considering that. Yes?
What if we could play polo?
Polo. The horses, they don't care. Can you imagine the horses in those uniforms, in those costumes?
Replace the horses with elephants.
Oh, elephants. Let's send elephants to the moon. Okay.
For one thing, when you're sitting on an elephant, the stick of the polo stick is going to be very long.
Yes.
The force will reduce, with which the player is going to hit.
Ah.
So when the force reduces, thanks to what you call as moments, so the ball size, even if it remains the same, or even if you increase it also, it's going to stay on the floor. It's not going to take off from the floor. So it's not going to fly, and the projectile motion is not going to come into picture there. It's going to be a linear motion.
So in polo, though, doesn't the ball leave the ground?
If you replace horses with elephants on the moon, probably it won't.
Okay. So these are some interesting features. We have to send our elephants to the moon, mero sati, mero hati. I mean, so we have to do that. And then we have to, we can play the sport indoors, so we don't have to give them uniform. Those space suits, you have to realize this about the moon also. If you play outside where there's no air, they wear those spacesuits, and if they're playing a sport and they fall and the spacesuit rips, they die. This is a high-stakes sport here. But maybe there's something with the polo, with the stick and the ball going, and maybe the ball will stay on the ground. If everything stays on the ground, it's good. Yeah, I want you to keep that idea, because don't forget, we still have to learn more physics. Yes?
I think the easiest sport to take there would probably be long jump. Just take a longer
The long jump.
Just take a longer pit.
Okay.
You may land a little farther, but you will land.
A little farther? 6 times farther. Oh, but it works. Now, of course, are you doing this indoors or outdoors?
Preferably indoors.
Preferably indoors, so you don't have to wear the uniform. So maybe it's just like soccer. Let's keep that, just like a long jump on the earth, let's keep that in mind, because I don't know how well we run on the moon yet. Oh, you have to run, right? You're assuming you can run the same way on the moon, because there's nothing here saying you can't run the same way. Wait till part 2. Yes?
I think the perfect game for the moon would be chess, because you're just using your mind.
Chess.
You don't have to jump or push or...
In fact, now the question is, chess would be it's not an Olympic game, chess, but some people consider chess a sport. Many people who like science think chess is a sport. But the question is, does it meet the criteria for a sport? If I turned on the chess game, would my nephew say, that's a sport? He might, because you would say, there's equipment, there's a field, but I know people who play chess without a board and without pieces. Pawn to king 4. Rook takes pawn. They play it in their heads. So now it's no longer a sport, because there's no equipment, there's no board, there's none of the criteria for a sport. And some people would say watching chess is not entertaining. So we have to decide, does a sport have other criteria, like your heart should beat fast and you should perspire a little bit? My son has told me, because we were looking at yo-yos, and the championship yo-yo person in the world, and he can do all these things with yo-yos, and he's a champion, you can see him on the internet, but he weighs much more than any other athlete. And my son said, if you're the champion and you look like that, it's not a sport. So that's one of the criteria he uses, unless it's sumo wrestling. Okay. So what we do when we teach this, because this is not just for one Friday evening entertainment, this is what I do for 1 month of school when I teach physics. Let's develop a sport for the moon. And for each of those sports things, it's not just one. There's experiments and data and analysis of these things. They make the diagrams at 6 times further and 6 times longer. They do the mathematics to see why it would take 6 times. But halfway through the chapter, I say, just like I said to you, please develop a sport for the moon. And we do that to give the students practice. We give that so students can see how difficult this is going to be, because right now I say, this will be easy, this will be easy, this will be easy. Then at the end of the chapter, it's like, oops, this is hard. So I want them to see how difficult it is. I want to remove some of the mystery. I also want them to see how this is like engineering design. In engineering design, you have a goal, develop a sport for the moon. You have inputs, we learn physics principles. There's a process, you talk to each other and try to develop a sport. There's output, you told me the sport, and then you get some feedback. And then you go through the cycle again. This is the second of the, they learned about this before they started, they learned about it now, they're going to do it again at the end. But let's learn some more physics. So, as we return to the sports on the moon, one of the things we can worry about is this object goes too far on the moon. It might even go into orbit, in fact. Now the feather, the falcon feather, was not a big deal. Falcon feathers don't weigh much. But every time they bring something extra on the moon, it costs a lot of money. They really don't bring extra things like, oh, you know, maybe I'll read these 3 books. No. You bring what's absolutely essential because it costs millions lakhs of rupees to get things up to the moon. And one year, on one of the 10 or so moon things, one of the astronauts said, I'm going to bring a golf club. And he had to sneak the golf club on because he didn't want to tell anybody he's bringing a golf club. This costs a lot of money. So that he could golf on the moon and have the longest golf drive in the history of human beings. But a golf, because on Earth, a golf ball can go 100 meters. On the moon, that's 600 meters. So one of the things we might want to do with our sport is tame the sport. Different balls bounce different amounts. So we have a tennis ball, and that bounces a certain amount. We don't play tennis on carpet, but it bounces a certain amount, and that's actually a regulation. I mean, if the tennis ball bounces too much, you can't use it. Too little, you can't use it. So it bounces a certain amount. A ping pong ball bounces a certain amount. A golf ball bounces a certain amount. One of the things, now, this is carpet. Golf balls bounce much higher than that. Not on tables either. So we should play golf somewhere else. But when a golf club hits the ball, it goes very far. It's going to go 6 times further on the moon unless we change something. We can change the ball from this to something that bounces like this, so it won't go as far. We don't want to change the swing because if you're a professional golfer or a professional cricket batter on the moon, on the Earth, you want to be able to play well on the moon. So you don't want to change how you hit the ball in cricket, but you want to change something so it doesn't go as far. So one of the ways you can do that is by changing the bat, making it out of foam or something softer, or you can change the ball so it's something like clay, so you can still play, but things don't go as far. So it's one of the modifications you might want to make to the equipment to tame the game so it doesn't go over the horizon on the moon. Friction. Friction on the moon. In the picture you saw, the lunar rover, that's the car on the moon. There must have been friction on the moon because the car moved. If there was no friction, like in a lot of mud, the wheels would have just spun, and the car wouldn't have gone anywhere. So seeing the car move on the moon is evidence there's friction on the moon. Now, friction is important in a lot of sports. In a lot of sports, you want to get from here and you want to run over there. And you need friction to do that. You need friction to run, and you need friction to stop. So the question is friction the same on the moon? So we have to do an experiment. We have to find out about friction on the Earth in order to understand friction on the moon. So here's an experiment we can do. We can take a spring scale and we can weigh how much something weighs on the Earth. And then we can pull it on the Earth and see what happens as we weigh something and then pull it. The pulling it will tell me how much friction if we pull it when it's on a surface. We can pull it on a surface and we can see how much it weighs, how much friction there is. So we do that. And here's what happens. We gather data, and we make a sketch of the data. And this is the graph we get. As the object gets heavier, as I add more and more weights to this or to a notebook or something, I can Nope, I don't think I have it. Oh, yeah. Yeah, I can take this book, I can hook this here like this, I can pull this on I can weigh it, I can pull it on a surface, then I can put a weight on it, I can pull it again, I can put another weight on it, I can pull it again, I can put another weight on it, I can pull it again. This is what physics people like to do. Put more weights on it, keep pulling it, and then we see, oh, look at the relation. As it gets heavier, it becomes harder to pull. Good. And then we can draw the best fit line and say, oh, it's linear. If you triple the weight, it gets 3 times harder to pull. Fine. That's on Earth. We expect the physics on the moon to be the same because we expect physics to be the same everywhere in the world. You know, when I got here, when I got to Bangalore, I didn't worry and say, oh, when I get to Bangalore, if I let go of the ball, which way will it go? I live in New York. You know, which way is the ball going to go? No, I still expect the ball to go down. Even if I go to New Zealand, where the people live upside down, I expect the ball to go down. We expect the laws of physics to be the same everywhere. We expect the laws of physics to be the same every day. And I'll give you an example of that, just so you get a sense of this. Every morning, people wake up, and they listen to the weather report. Is it going to rain today? Is it going to be cold today? Which direction will the wind be today? And we listen to the weather report because maybe we have a party to go to, or we want to know if we should eat outside or what we should wear. Should we bring our umbrella? We listen to the weather report. We never listen to the gravity report. We don't wake up in the morning and say, today, when you let go of a ball, it's going to fall straight down. Oh, today when you let go of a ball, it's going to fall down and to the left. Oh, today when you let go of a ball, it's going to go up and down, and then to fall. No, we don't need weather reports, we don't need daily gravity reports, because every day it's going to be the same. That's what we like about physics. Every day it's the same. It's what some people don't like about physics. Oh, physics, it's always the same. In fact, you know, this idea that like, really, that also works by energy, that also works by momentum. Physics is so limited. It must be so boring. There are only a few ideas you have. But literature, oh, we can write books about anything. But in physics, you can't make, and some people like that it's limited, and other people say, I don't like that. So we expect that friction will work the same on the moon as it does on Earth. But here's the problem. You see, if an object weighs 600 newtons on the Earth, you can go up to this line and say 600 newtons up, how much friction is there? So we go up 600 newtons and we see how much friction there is. But on the moon, it's only going to be 100 newtons. So how much friction will it have? Oh boy, very little friction. People are going to be slipping and sliding all over the moon. When you try to stop, you're just going to slip out. When you try to start, it's going to be like starting in wet mud. So now, when we used to play kabaddi in Nepal, they used to take the water and make it all a muddy field. And it was just, is that how you do it here? Is it a dry field or a wet field? Dry field. Try it after you make it muddy. It's a much more fun game. So, what we have is that the friction is going to be 1/6 on the moon. So let me show you again how I do that experiment in class so you understand it. The instructional model I use when I teach is called the 7E instructional model. So we have these steps. I try to engage the students. I try to find out what they already know. I then have them explore something. Then they have to explain it to me. Then we elaborate, and then we extend. And all through that, I evaluate them. So here we go. I start off with this picture, sliding on the moon. This is a baseball game because we play a lot of baseball in America. And there's baseball on the moon, and you can see the astronaut slides into second base and misses the base because he keeps sliding. We ask the student, what do you think is happening? They don't know. They haven't done the experiment. At the end of the experiment, we will say, what do you see now? And they'll better understand this. And then we ask the question, as I asked you, the lunar rover proved there is a frictional force. How and why are frictional forces on the Earth and Moon different? So now I'm going to elicit. I'm going to try to find out what do they know about friction. What do they think they know about friction? I don't correct them. I just listen. And then they do an exploration, the experiment I showed you. We lift the box, we pull the box, we put weights in the box, we do it over and over again. They make the graph, they explain to me what the graph means. Then we do the analysis of the graph for the elaborate, and we say, now let's take what would happen on the moon. It'll weigh less on the moon, so the friction will be less on the moon. And then we ask these 4 essential questions, which I spoke about last year, I think. Did I speak about this last? I think I may have. What does it mean? How do you know? Why do you believe? And why should you care? What does it mean? How is friction on Earth related to friction on the moon for 2 identical objects traveling on identical surfaces? How do you know? What observations do you make to support the conclusion that the frictional force on the moon is 1/6? What experimental evidence you have? What observations did you make? Why do you believe? Physicists assume the physics on Earth and Moon are identical. If you could travel to the moon, how would you measure the frictional forces? And we hope students would say, oh, I could weigh something, pull it, weigh something, pull it, weigh something, pull it, and make my graph on the moon. On the moon. And then the why should you care? This incredibly important question of relevance for students. To make the science relevant, not one day this will be useful to you, but this should be useful to you now as a teenager in Bangalore. And in this case, why is it useful? Because they've been hired to develop a sport to be played on the moon, so they better know about friction. And then we give them some homework to do as part of the evaluation. Now, you have to be able to walk and run in sports. And so the question is running or walking different? So who has the shortest legs here? Now, I just want you to walk back and forth, just so we can watch you walk back and forth. Very good walker. Now watch me walking back and forth. Now let's walk back and forth together. You stand over here. You can see me here. Okay, thank you. It's hard to see with him walking and me walking, so we need a model to help us understand walking. Your name is? Rishikesh. Rishikesh. Okay. So here's his leg. Here's my leg. A model. So his leg moves like this when he walks. You see, we would get very tired if we pushed our legs, but actually when we walk, I go forward, and I let this leg swing. Then I go forward, and I let this leg swing. And I can do it a little more gracefully, but that's basically it. Let it swing, let it swing. Let the leg swing by itself. Let the leg swing. Now, here's his leg swinging. 1, 2, 3, 4. Here's my leg swinging. 1, 2, 3, 4. And if we take somebody who's only 1.5 or 2 years old, you see them go down the hill and their legs go, they're so short, the legs go so fast. So, what does this have to do with the moon? Well, my leg swings back and forth. Why does it swing back and forth? Why does the leg, if I put it up here and I let it go, I can't hold it here forever. Why is it going to go down? Gravity. And what do we know about gravity on the moon? 1/6. So the leg does not go down, swing like this. It swings 6 times slower. So now when I try to walk on the moon, I have to wait for my leg to move. And that's why they move that way. It's not they're waiting for their leg to, and when they do that, they say, oh my goodness, maybe there's a better way to move.
But excuse me.
Yes.
Wouldn't lifting the leg be 6 times easier? I have to first lift
Yes.
it.
But
There's some cancelling.
yes, there's some, but usually I still wait for it to swing. I still wait for my leg to swing. I can force my leg like when I run, but you get very tired very quickly. And when you're in the air trying to move, you have no control. You have to wait for gravity to pull you down. So we do this experiment. The students will do this experiment and they'll measure the period of this, and then they'll take a longer rod and they'll see how long it comes down, and they'll make a graph, and they'll do this with all these different rods. And then, and this is very hard, we then have them try, so if this one is the same length as my leg, I then try to sit on a table and move my leg back and forth to see if it really does move the way this would move. And it doesn't. The model's not that good. Because what I need for a model is the upper part of my leg and the lower part of my leg, because my leg has this pivot. And then I have this big weight at the bottom called my foot. So it's a model, and we try to do simple models, but we want to look at more complex things. We make the model more complicated if the simple one isn't working. So they do the experiment, and then they can work on the equations and see why it's different than a pendulum, which is a string with a big mass. And they can do the mathematics and measure the period of the pendulum. But basically the idea is, how am I going to walk? So if I can just show you that film again. Slow fall, he comes down slowly. There, look at him walk, just that leg is just moving slowly back and forth. Swing that leg. Don't forget, car racing is also a sport. Okay, you can try car racing. Less friction. And I think this is what I wanted you to see. Not this film. Right in the next one. See, he's trying to walk. It's oh, look at that! I figured out a way to move up, then down, up. And see how slow that is? But the jumping turns out to be easier than the running. So again, every time I see it, I can't believe we walked on the moon. I just cannot. And I know I can't believe it because it's so fantastic and so wonderful and so exceptional. Some people don't believe it because they think, we get better special effects in our movies. This must have been a movie. It was not a movie. So, we're okay. Oh, Remember dropping the feather and the hammer? They felt the same rate outside. But you're telling me a lot of your sports you're going to play inside. So, let's take a look at what happens inside. So I take a coffee filter, one, and I let it go. But if I take a bunch of them, they all reach a constant speed after a short amount of time. But this one, slow constant speed, when I have a lot of them, a big constant speed. Also, I can take a small one and a large one. Oh, not too much difference, but some difference. Some difference. That one's a little faster. I can have a bunch of them. So the point is that things reach this slow speed if they don't weigh very much on Earth. Now, on the moon, nothing, you don't weigh as much. You only weigh 1/6. Now, just like I said, you will have a hard time lifting me on Earth, it's not so hard to lift me on the moon because I'm only 1/6. My arms, I can't lift somebody as big as me on the moon, on the Earth, but I could lift somebody as big as me on the moon easily, over and over again. My arms are that strong. So maybe I could build some wings and fly on the moon, glide on the moon, flap my arms on the moon and stay up. I can't do that on Earth because, well, the airplanes can do it because they have much bigger arms than I do. But I can't do that because my arms aren't strong enough to hold my weight, even if I put filters on or wings. But on the moon, I might be able to. Now, that's where we need the math. The math will tell us if we can do it or not. And that's why we use the math to say, I think you might be able to fly. No, we want to know, can I or can't I? And the math tells us that. We don't do the math. We don't add the math to physics to make it harder. We add the math to physics to make it better to understand. It's a tool. So anyway, here we are. What sport, what changes, rules, fields, scoring. So let's go over the physics you've learned. This is the physics you learned in the first half. All objects fall at the same rate. Objects take 6 times as long. Objects weigh 6 times less. Projectiles travel 6 times as far. People can jump 6 times higher. You also now know that you can tame the collision by changing the bat or the ball. Friction is 1/6 on the moon. People are slipping and sliding. Running, walking, bounding on the moon, it's a whole different world. And air resistance, outside there's none, and inside there's plenty. So now, 4 minutes again, develop a sport that we played on the moon. Go to work. So who solved the problem? Yes, tell us.
2 ways. One is to take away the concept by, her idea of taking something like a fluid, which means that I can control viscosity, which is the equivalent of friction, and I'll control buoyancy, which is the equivalent. So I can do all the swimming events.
So swimming, you think, is exactly the same?
You can go and create similar structure.
Now, of course, it's going to be indoors. Because there's no air, there's no water either. It evaporates.
Well, yeah, evaporation.
So you think buoyancy will be exactly the same, even though your weight is different?
So you'll calibrate buoyancy to.
Will you? So we know that your buoyancy is different in water and in salt water.
So you calibrate.
And your buoyancy on the moon and the Earth will be the same, or different?
You calibrate it to get. It's different. It's different.
Oh, and so if it's different, how does that affect swimming?
Underwater.
Oh, underwater swimming. Can you go underwater on the moon?
You're wearing the...
No. Inside, indoors. If your buoyancy is, you can't go underwater within mercury. Mercury, you're almost standing on it. It's so dense. So it's an interesting question, but swimming might get away with some of these.
So two ways, we only looked at how do you negate that process.
Yeah.
So two ways we came up with. One is to look at fluid that would go and negate.
Yep.
Another one is to create a constant magnetic field, which would replace the equivalent of.
We'll wear a lot of iron and have magnets on it. Another interesting way of doing it. So let's try it on a sport. So I like that swimming. Somebody else solve the problem. Yes.
So you talked about friction reduces to 1/6 on the moon.
Yes.
Now, if I remember the formula correctly, friction is given by mu into m into g, where mu is the coefficient of friction between the two surfaces which are in action. Right. So if we can control for the coefficient of friction, so that will take care of, say we put grooves in our shoes.
Yes.
Spikes in our shoes. So if we increase the friction, so we can control the horizontal motion. And if we control for the mass, right, increase the mass, so that will control for the horizontal motion. So we can apply these to in cricket and badminton. So increase the mass of the shuttle and control for this groove, so that we can play in a same space in a similar way that we play on the earth.
Okay. So the sport is badminton. Nice sport. And he's going to control the mass of the shuttlecock. And then he said, I still have this friction problem, so I'm going to change the surfaces to change the amount of friction. Maybe we'll make the surface Velcro, and we'll put Velcro on the bottom of our shoes. But it's a good idea. He's saying, I need friction differently. How can I do that? And he found a way to do it. And that's what we have to do in all the sports. And then he told us about the coefficient of friction and mu and force, and it was very nice. Somebody else solved the problem. Yes?
You could play carom board on the moon.
Carom ball.
There's less friction, and so it would make it easier to... I mean, I don't know if it would be easier, because I think it would be another skill altogether to put the right amount of force on the moon, because the friction is so much less.
And you just have to help me with what carom ball is. Billiards?
Billiards, you use the big ball. In carom board, we have a small wooden.
Okay.
There's a spiker, you hit that.
Like that? Maybe. The friction is different, or you can change the friction by changing the surfaces, and everything stays on the surface in that game. So you don't have to worry about it flying off and stuff like that. Maybe. Now, is this a game you like to play very much on Earth? When I turn on the television, do they have this game all the time? One more person. Yes, how do you solve the problem?
So two people already tried solving it, looking at a game which is played on the horizontal.
Yes.
I think ice hockey really fits very well in all of this, because it requires low friction. So you prepare the moon surface only to basically play ice hockey, and almost everything works because nothing lifts off the ground.
But in ice hockey,
They're not moving their legs; they're actually skating. So there's no movement of the legs also that is required there.
There's no movement
in the lifting sense of it.
Well, I think the ice hockey people do lift their legs, and also when they want to turn, they have to get friction on the side of the blades. So it's interesting, and it's another good idea to pursue to see if this would work. Some people say, "Oh no, I'm going to play basketball on the moon." I say, "But no, the ball will go so high." It's like, no, the ceiling's only going to be this high, so you have to hit it off the top. Nothing's going to go far because you're going to have the bottom surface and the top surface. So there are lots of ways, creative ways, to change the sports to be anything you want to play. So now let's talk about how the students do it, the educational part of this. So this is part of a curriculum which I worked on for many years called active physics. And the whole idea of active physics is every month the students are given a challenge. 1 month it's develop a sport to be played on the moon. That's why they learn about motion. Another one is make a light and sound show to entertain your friends. So they learn about stringed instruments, and they learn about color and reflection of light. Another one is design an improved safety device for a car, and they learn about energy and momentum and impulse. Another one is build an appliance package that can be used by poor people who don't have electricity from the grid but can only use a small wind generator. But every month they're given a challenge. And in 1 month, they have to try to solve the challenge. The first day we say, what would the criteria be to get a good grade? In this, it has to be a sport, it has to be entertaining, you have to explain the physics, you have to know that friction is different and things go further. And then, after we show them that, the scenario, colony we set up on the moon, here's the proposal to ISRO or NASA. Here's the criteria for success, they discuss that. And they have to show these things. Then we show them what we think is a standard for excellence, but they look at it and say, no, we had other things, or, oh, that's a good idea, I didn't have that. So this takes less than one class to describe the challenge. It takes only a few minutes to go over the rubric, or how will you be graded. And then for 4 or 5 weeks, we go through, like the friction section which you saw. What do you see? What do you think? Investigate, physics talk. We ask the essential questions. We then say, how can you take that physics and change your sport? Every time. Not twice in the month, but every time, every 3 days. Then we go through the physics they learned in the activity. The blue is for those students who want to do more than is required. And you can see that there's physics concept and then there are equations, because this is a secondary school physics course, so all of the equations you need are there and they practice those as well. We can do some of the equations here after everybody leaves if you want some problems to do. We can do that. Some people think that's more fun than what we've been doing. Then we go through the engineering design challenge and we do the chapter challenge again. The output, the process, the feedback. And then we say, oh, this physics you learned, it's not unique to physics. The idea of mass, weight, and gravity is important in biology. You know, when you put a seed in the ground, we want the plant to grow up. How does the plant know which way is up? If the plant grows this way, it's going to die. It has to grow up. The seed must somehow know which way is up. There must be something in the biology to do that. In chemistry, we worry about how gases are affected by gravity. There's no air on the moon because the gravitational forces can't hold the air on the moon. And in earth science also work. Air fluid and resistance. Oh, we study a little air resistance here. In biology, the movement, the viscosity of object, everything in biology is liquids moving through the body. You have to know about viscosity. So this is just to help students. If you've studied chemistry, this reminds you, here's some physics that they might not have told you. If you're going to study chemistry, you say, oh, you'll be able to use this when you learn chemistry this year or next year or the year after. And then these are people. We tell them about people who actually do this work. Here's Neil deGrasse Tyson, who works at the planetarium, Michio Kaku, who's a writer, and Jill Tarter, who spends her life trying to look at signals to see if anybody from out of space, from way out there, is sending notes to us and saying, hey, come on, let's. And then we give them a practice exam, because that's part of passing the state exam, is to know how to take exams and answer those questions as well. Now, what's different about this and our typical education? The challenge does a lot of wonderful things. First of all, it's when you were discussing what kind of sport on the moon that you said, you came up with an idea and said, no, don't forget friction's less. No, what about this? Like, no, it's going to go 6 times further. You were reviewing the physics. You were learning the physics. You were trying to transfer the physics. And when you do that, you take ownership. When you heard about swimming and you heard about carambole and you heard about you start saying, oh, that's right, friction. Oh, the Velcro on the, change the surface. You heard about the same physics in different sports, and by doing that, you learned other examples, and you will remember the physics better. Maybe you didn't get the physics with football or rugby or cricket, but swimming. Now I understand the physics. Motivation. The students are motivated. They like doing this. Expertness. They're experts, not in the physics. They're experts in cricket on the moon. Their interest, their culture. In America, nobody's choosing kabaddi. In India, nobody's choosing baseball, American baseball. So you can choose what you're interested in. And let me show you why we know this works. We know there's an independence of chapters, fresh starts, limited horizon. Their relevance. Why are we learning this? They know why they're learning it now. There's some research that's been done about what engages students intellectually. So they asked 1,000 students in America, when you're in school and you enjoy school, what's going on? Not science. You might be in history. You might be in English class. When you're enjoying school, what is going on? And the students said, we get to pick the content. Now, as a physics teacher, it's like, no, you have to learn about friction. You have to learn about this. But I didn't tell you what sport you had to do, and that gives them a sense that they're choosing the content. They say they have time to wonder. I like school when I have time to wonder. Sport on the moon, light and sound show for your friends, improved safety device for a car, a museum display. They're wondering. I wonder. I wonder. Subject topics had a strange quality. There was something strange or unusual. Make a light and sound show to entertain them. Oh, a sport on the moon, that's interesting. Students said in America, I think it might be true in India also, students said that they liked school when teachers permitted, even encouraged, different forms of student expression and respected student views. When you said swimming, I said, oh, swimming doesn't count. You can't do swimming. Carrom ball, I don't know that game. You can't use that one. No, I accepted what you wanted to do. I permitted it. I even encouraged it. Teachers were passionate about their work. That has nothing to do with the content. Teachers should be passionate. They should love their subject matter. And students said, we like school when we get to create original products. They like being creative. And if you only give them physics problems like an object is thrown at 10 meters per second at an angle of 14 degrees, where does it land? And a student says, it lands 13.8 meters. No. 13.7 meters. Yes. This is not very creative. If everybody gives you the same answer, it's not, that's my definition of creativity. If I ask everybody a problem here and everybody gives me the same answer, it's not creative. It's not, there's no creativity involved. And they like when they got to create something and share it. They also like when they do something. Can I participate in a political action? Can I write a letter to the editor of a newspaper? Can I do something, help with the homeless, help with the poor people? I want to do something. I want to change the world. I want to be a participant in the world. I don't want to just answer questions on a test for the state exam. And the student said, I like school when you don't know what I'm going to do, when the teacher doesn't know what I'm going to do. And in the sport for the moon, I know all the sports. I mean, I know all the physics, or a lot of the physics, but I don't know what sports you'll choose. Right now in America, we're struggling with 3 dimensions, a new way of looking at science instruction. We focus on science and engineering practices. That's doing the labs, doing all these things. Then we have the cross-cutting concepts like that all science deals with, looking for patterns, using models like my model of the leg, cause and effect. If this happens, then this should happen. That science is the same today and tomorrow here and in America. And the core ideas, friction, gravity, trajectories, oscillations, all that stuff. And what they're saying is, don't teach them separately. Teach them all together every day. And that's hard. People don't know how to do that. But we're trying, and we think active physics is one way to do it. So here's a picture of disciplinary core ideas. This is my picture of disciplinary core ideas. This is my picture of science and engineering practices. This is my picture of cross-cutting concepts. So let's take that picture of disciplinary core ideas. Then we'll combine that with my picture of science and engineering practices, and then I'll combine that with the cross-cutting concepts. And the pattern I get is so much more beautiful, so much richer than any of those separately. I can still see the orange, the disciplinary core ideas. I can still see the green cross-cutting concepts. But together I see new shapes. I see this shape. I see the diamond surrounded by 4. I see all sorts of new shapes. And it's richer. And that's what I think we want for science instruction. So this was an example of project-based learning, what we call project-based learning, and we've been doing it for a long time, active physics and active chemistry. It's a different way of teaching. We know the students do just as well on the state exams, but we also know they like science more. We also know when adults see this, they say, I wish my science class had been like that. So that's the dream. The dream for learning, the dream for science, the dream for education. And so I'd like to dedicate this talk to Kalpana Chawla, one of your heroes. I think we can live in Kalpana's dream in science and in education. Thank you. So I can answer questions if you have them, but first, I need you to come here, my helper, my big helper. I'm going back home, and I don't need these when I go home. I don't need these balls when I go home. I don't need this masking tape or this tennis ball when I go home. I don't need this string or these coffee filters when I go home. I don't need these rods when I go home. So can you take care of them for me? They're yours. Maybe you can do some experiments. You can play with this and do some experiments like we did here. Yes?
The problem for us is we don't have many teachers like Ramji who inspire the students in this country at the very primary level. And many of our teachers also behave in a different way. Like when I was 10 years old, my teacher brought a big globe and kept on the table. Told me, this is the word. I asked him, how do you know?
Ooh, a rambunctious student.
The answer I got was, he had a skate, he gave a hit.
Yes.
I kept quiet.
Yeah.
Then I thought, I must find out whether the globe is this.
Yeah.
It took 3 years for me to find out. But 15 years later, I walked and found out the word was this. I did.
And it only took you. And it only took you 3. It only took you 3 years to walk around the world to find out you're back where you started. So it's very interesting. It's a very profound remark. First of all, it turns out that it doesn't matter how good or bad the school system is. There are some students like you who will succeed in spite of poor instruction. Everybody here had to learn many things by rote, but because of our parents, because of our own desire, we learned. But everybody doesn't. And the teachers of the students were those people who learned, and they said, oh, I learned that way. The students should be able to learn that way, and if they don't, I don't care about them. So that is a problem. I think we have many teachers like Ramji. I think we just have to help them to see how to inspire. And we have to get them away from you learn by repeating, by repeating, by repeating. They have to see a different way of teaching, and they have to try it. Not every day, because that task is too great. But could you try it once a month? Teach a lesson like this. And then after once a month, if they do it 10 times in 1 year, they will get better at it, and the next year they can do it 10 more times. It's a gradual growth in learning how to be a teacher. I think the teachers are working very, very hard. Many of the teachers, most of the teachers are working very, very hard. But they don't have the opportunities to learn how to teach differently, and that's what we're trying to do. That's what Azim Premji Foundation is trying to do.
One more problem for us. We think everything will happen in the next birth, and we also think what happened now is the consequence of previous birth. How do we change that mental attitude?
Well, That's certainly a social justice issue. You see, I never worried about my own children because I have I have a very good education. My wife has a good education. I knew when we ate dinner every night, my children would be learning because they would be hearing good conversations. But we have many, many children in India who are poor, and their parents don't have education. They don't hear that. And so it's very important. It's crucial that those students are given opportunities to learn now. And one of the reasons I like science is if you can write down the equation, I don't care if you're rich or poor or who your parents are or who you know. Physics is not history or politics. If you can write the equations, you can advance. And I think, again, that's what the Azim Premji Foundation is trying to do, is trying to make sure that everybody has access to a good education and understands that they can succeed. So we're not going to solve it tonight. I would need another half hour. I don't have a half hour. Are there other questions? Yes. And then 1, 2.
I met up with a person who's an NRI, a person who settled in the US a long while. He had his son here and he's doing some rifle shooting. Sat down and talked. He was in the US for about 20 years, his son is around 10 or 12 now. So he brought him back here. So I said, why have you brought him back from California to India? He said, oh, my son growing up there till 12th standard, this is not my opinion, I want you to comment on that. He says, till 12th standard, there is no education, they're just fooling around. And the chap doesn't learn anything, but here it's much better. But I'm going to take him back to the US for a university college education.
So a lot of people wonder, and they say, we look at all of these countries and we see on the international examinations, the United States doesn't do the best. Finland does the best, Singapore does the best, America is number 16 for the average student. There are pockets in America where we're number 1 in the world. We would be number 1. If it was just the state of Massachusetts, we'd be number 1 in the world. But we have 50 states, and it's a big country, and we have poor people and wealthy people. So a lot of people worry and say, oh, those American students, they don't learn that much an undergraduate. Somehow in college, now when you go to university here, you begin a major almost immediately. In America, you don't get to begin a major for 1 or 2 years when we catch up. And our PhD programs are the best in the world. I'm not sure how it all works. Right now, China, we have little 3, 4-year-olds who are learning English perfectly. They learn so much. They learn by rote, but they learn everything. We have different countries where students are very good. But all of these countries seem to say, to me, they say, how do you get that creativity in America? Maybe it's because we fool around a lot in class. When I go to a government school here, 70 students in a classroom. This morning I worked with private school teachers. They told me they have 30 students in a class. In the government school, 70 students in a class. But one of the things that struck me was they all sit there very nicely. In America, 70 students, they poke each other, they do this. I go to schools in China, and all the children are well behaved. They don't talk out of turn. They don't challenge the teacher. In America, every child is challenging every teacher. The hardest thing for a first-year teacher in America is the class management because the kids are just jumping all over the place. Maybe it's the challenging every teacher which makes us creative. How am I going to get this teacher to be? I once had, in my class in secondary school, I once asked my students, I said, you give me such a hard time. There's a teacher down the hall, you never give him a hard time, and you know he's a terrible teacher. And I said, why do you give me a hard time, you don't give him a hard time? And they said, oh, he's too easy, we can make him cry. You're a challenge. And it's those kind of challenges. I think that the person might not have wanted to say this, but there are other reasons you bring people back home. I have a friend in Boston. Boston has a large Nepali community. About 14,000 Nepalis live there. And so I've met some of them, and I can speak Nepali, so we have a good time. And there was a book that was published in English, a translation. And it's a story that every school child in the 9th year, ninth class, reads in Nepal. And I told him about the book, and I said, do you remember reading this? He said, of course, everybody reads this. And it's a sad story about a poor person living on a farm, and then he borrows somebody's bison to help him with the fields. The bison dies when he hits it, and so he's going to lose his land. It's Dostoevsky. It just gets worse and worse and worse. And it's a wonderful book. And he said, can I borrow the book from my son? My son's grown up in America. And so I said, sure. He takes the book, and a few weeks later I said, oh, how did your son like the book? And he said, I have to take him to Nepal. He doesn't understand the book. He doesn't understand the world. So he might have brought them back because he thought his children did not understand. He might have said they'll get a better education here. But education doesn't just mean about books. It means about culture. It means about the way you deal with people. So I've tried to give you the educational reason, the cultural reason. There was another question. Yes?
Just out of curiosity, has there been somebody who's come up with a sport and won that challenge? It's been going around for a while.
So to win the challenge means NASA or ISRO has to say, yes, we will use that.
Have they met all the
Yes. Yeah. With the low C. Yeah, people do it, but I give them in school more time than this, and of course, to really win, you have to do the mathematics, you have to do other things. There are other little problems which I didn't want to discuss here because this is a science lecture. But when you go to the moon, you live there for a long period of time. What kind of government do you want when the government controls the air you breathe? There are all sorts of other issues we have to worry about as we think about living on the moon. And I don't know if any of you, I think it should be in Bangalore now, but the movie The Martian with Matt Damon. Has anybody seen that? It's wonderful. It's extraordinary. It's just a homage to science and technology and even botany. And it's just a wonderful movie, and I would... The book is wonderful. The book has some good humor in it. The movie is done well, and they're both extraordinary. Yes?
I have one question. So when you teach, does sometimes religious views stand in the way when you teach?
How would they stand in the way?
So if someone has some kind of unscientific way of explaining things, and if they are already indoctrinated in their children, does it affect with the kind of questions that kids ask in the class?
So that's always a question of why do you believe? And, so you can have competing explanations for something. In the most extreme cases where a child says, no, I will not believe in biological evolution because my religious book says the world was created 5,000 years ago, then you can say, I don't want to change your beliefs. I just want you to learn the science. You don't have to believe it, but you have to learn it. So that's in an extreme case. But often the question is, what do you accept as evidence? So we don't even have to worry about religion, we just worry about politics. I wondered during the last presidential election, we have one party in America that believes that there's climate change. We have another political party which says, no, there's no climate change. And they have that belief for certain political reasons. And I always thought that, why doesn't somebody say to one of these people, well, what evidence would you need to convince you there is climate change? So we haven't passed your threshold to believe in climate change. What would I have to show you to believe that there's climate change? But I worry that the answer might be, show me in the Bible. And then what you're saying is, oh, so there's no evidence, so we're not talking about science anymore. It's something else. There's no way to change your mind, so then we don't have to discuss it anymore. So that's that science, religion, beliefs, politics. If somebody says, you can never change my mind, then we needn't discuss it anymore. But changing people's minds are very, very hard. It's very hard. Yes?
When you live for a longer period on the moon, then
Yeah.
long-term living probably would not facilitate any sports because it may not be physically fit enough to do this activity.
Well, you're absolutely right. And in fact, the moon, we've only stayed there for 3 or 4 or 5 days. But in the space station, people have been there for 6 months and 7 months, where there's zero gravity effectively. And we do know, because they take medical tests all the time, the bones decalcify. They don't produce as much calcium because you don't have to hold me up all the time. The muscles atrophy because they don't have to be as strong. And in fact, I just read in I Wonder that when I stand on the earth, the blood goes to my feet, gravity. And when the blood has to come up to my heart, there has to be valves in the legs to move the blood up. Now, on the moon or in space, you don't need those valves, but they're strong, so the astronauts get puffy, their chest gets big because more blood is going up there until they get used to it, until their body gets used to it. So, but they do exercise, even in the zero environment. They have ways to simulate gravity because you don't want to. When they come back to Earth from 6 months in the space station, yes, they're wobbling. They're wobbling. But, because they've been weightless for 6 months. But what I've heard is you say hello to them, you shake their hand, you never give them a baby to hold. Because in space, you hold something like this, and when they show you making a sandwich on the moon, in space, they take the pieces of bread, and they take a piece of bread out, and they put it here, it just stays there. They take another piece of bread, they put it here. Then they take the jar and they open it up and they take the butter out and they spread it, then they put that, and everything just sits there in space and they do this. And you get used to that. That becomes your world for 6 months. So you come to Earth and they give you your baby who was born when you were there, and you take the baby and you say, oh, I want boom. So they're very careful about that. It's amazing how we get used to things. Oh, I was going to say, if you want to play a trick on someone, if you want to see somebody, the globe, that teacher said, here's the globe, here's the earth. Take that globe and put it upside down. So the Antarctica is on the top, so that Africa is on the top, so that New Zealand on top. And students will say, no, your globe is wrong. It has to be we're on top. And you say, really? What do you mean by that? So it's interesting. And if I come to India and I say, I'd like to buy a map of the world, a flat map of the world, where is India? Right in the middle. When I go to Japan, I say, I'd like to buy a map. Japan's in the middle. And the United States in the middle. Yes, do you have a question?
I don't know if you have worked in or seen school environments that typically the change like this would be slow, right? So for example, if there is a program in science that is very different from, say, how other subjects are taught, how does that transition work for such environments? Because that's one of the things that a lot of schools are challenged with, that one department is probably doing better than the other.
Yeah. So we want to make sure that whatever instruction we give the students can also pass the state exams. And so we have to ensure that. What we have found with active physics, with the research we did, was yes, they passed the state exams, but we find that the women and the poorest students do better than with the other one, while the best students do the same in both. So it's very interesting. I don't know, I'm not answering your question?
No, so what I was saying was that, say for example, we are teaching science through this program,
yes,
and then we are also teaching history through a more traditional approach, right? So children would immediately start seeing the difference in one class over the other class. And so what kind of a result or a resulting environment does that create, and how does school manage that?
So I don't know, I can't compare the science to the history, but I can tell you that when you have a teacher teaching physics this way and another teacher teaching physics or biology the rote method way, the students know right away, and they start speaking to this teacher and hopefully start making demands. because that's another way to get change. Or if they've learned physics this way and then the next year they take another science and the teacher to say, no, why don't you teach that way? Tell me why this is important. You know, it would be wonderful if students asked, how do you know the earth is round? How do you know that? What's the evidence we have? And if more students start asking that, we make change that way, from the ground up. It doesn't always have to be from the top down. But it's difficult to empower students, and we have to encourage them to ask the questions and not discourage them.
Can I ask a political question?
A political question, okay.
America teaches democracy to the rest of the world. Why America has never elected a woman to the White House?
We elected a black man to the White House. People in all of the old movies, when they always said they'd have a movie in the year 2100 or, you know, some Star Wars movie or whatever, Star Trek, you know, they have these movies of the future. And in the future, there was always a black president. And you'd say, oh, a black president, that's way in the future. We've elected a black president. That in America is quite a big step. And there'll be a time when we elect a woman.
Where do you find the creative student? Do you find them in the first bench, last bench, or outside?
Where do I find the creative student?
First bench, last bench, first row, last row.
Oh.
Where do you find them?
Are you trying to get me to say the people who sat in the back are somewhat deficient? Is this right? He sat up front and he said, aren't I good for sitting up front? There has been some research on this, and it turns out that students who sit in the front do better in school. Now, is that because there's something about the front of the class, or is it something about the people who choose to sit in the front of the class? If I meet a child, I said, I don't know, but sit in the front anyway. Just please sit. So that. But what I do in my classes is I assign seats to the students, and every 6 weeks I change the seats so that everybody has a chance to be in the front and everybody has a chance to be in the back.
No, what I meant by a front bencher is it's like a metaphor. It's like a guy who's always studying. You could assign that front bencher to a nerd, somebody who's behind books and exams and has to score to get ahead. That sort of a guy. And a backbencher is a guy who has an exposure. I told you there is another class of people who are never in the class and they do well in exams and they have knowledge. So who's creative? That is the question.
Excuse me, in our school we don't have a front and back benches at all. We all sit in a circle and every 15 days once or once in a month we just change our.
So he was saying it's a metaphor for what kind of student is the most creative. The creative student is the most creative student. I don't think there are specific attributes that make somebody creative. Yes?
Yeah, so the answer could be in Indian terms, creativity does not depend on the vastu of where people are.
Okay. Thank you. It is a few minutes past 7. I know people have other obligations. Let me turn it over to Giri.